Dear friends, welcome back to Turbomachines class, session 3 of module 1. In the last session, we had the discussions about a particular quantities, the unit quantities. The unit quantities are the most important quantities which has to be defined for a particular turbo machines. They are the quantities which are warp time when the head on the turbo machine has been reduced to 1 meter. So, and such related issues already we have discussed in the last session, in the second session. Now I am introducing the concept of the specific quantities. The specific quantities are very important quantities for a respective turbo machine. There are three important specific quantities. I will summarize this entire session through these contents. One is the introduction to specific quantities, the specific speed of a turbine, the specific speed of a centrifugal pump, and the significance of this specific speed. So all these speeds, so all these quantities, it may be a unit quantity or it may be a specific quantities, all are very important in the field of turbo machines, because using these particular quantities, the people used to recommend a turbo machine for a particular conditions. So that's why we have to think about how we can define the specific quantities of a turbo machines. At the same time, how these specific quantities can signify the usage of this particular turbo machines. Now let me talk about this specific quantities. As I said that the specific quantities are the most important quantities in evaluating the performance of a turbo machine. A turbo machine need not be a turbine. A turbo machine may be a turbine or it may be a centrifugal pump. Therefore, the specific quantity is the specific speed. The specific quantity is the when we speak about a specific quantity, particularly the specific quantity is nothing but the specific speed, which will characterize the performance of both the aforesaid machines. As I said that turbine is available, centrifugal pump is available. Therefore, the specific quantity is the specific speed of a turbine. The specific quantity is the specific speed of a centrifugal pump. Therefore, the specific speed of both turbine as well as the centrifugal pump must be studied for the clarification of specific quantities. Now let us define the specific speed of a turbine. See, the things are very specific in this case, as the name is indicating very specific, because we are very much specific about two important parameters in turbo machines. One is, say, depending upon a type of a turbine. So we know that what is the objective of a turbine? The main objective of a turbine is to develop a mechanical power. Very important. Therefore, the power is one parameter. At the same time, if we need to develop a power, we must have an effective head on the respective turbine system. Therefore, head and the parameter are the two important parameters we have to keep in mind while defining the specific speed of a turbine. Therefore, the specific speed of a turbine can be defined as the speed of a geometrically similar turbine which is working under unit head developing 1 kilowatt of power. Very important concepts. When the head on the turbine is 1 meter and the power developed by the respective a turbine is 1 kilowatt, under that situation, the speed at which the turbo machine is running is called the specific speed of a turbine. And we are talking about a geometrically similar turbine. Geometrically similar turbine is nothing but the turbine which is similar in all dimensions. We have discussed this particular geometrical similarity only with the help of the similarity concepts, that is the similitude. Using the dimensional analysis, we can define the meaning of geometrically similar turbines. So let us see how we can derive this specific speed of a turbine. Now let us consider, let capital N is equal to the speed of a turbo machine in RPM. H is equal to head on the respective turbo machines. Capital V is the absolute velocity of the water through which the turbo machine in meter per second. A is equal to area of the flow, and Q is the discharge through the machine. Eta naught, eta O is equal to overall efficiency of the turbo machines. P is the power developed by the turbo machines. Right? So we know that the tangential velocity U is always proportional to the absolute velocity of water. We have already discussed through the respective concept of turbo machines. Therefore, U is directly proportional to V, but we have V is proportional to root H, and hence I can say that U is also proportional to V, V is also proportional to root H. Finally, we have the tangential velocity of the runner, U is equal to pi dn by 60. From here, see, this one concept we have to observe in this case is, while deriving the unit quantities, when we write the expression U is equal to pi dn by 60, there we maintain capital D is also a constant. But in a specific speed of a turbine, geometrically similar turbines we are talking about, geometrically similar turbines. Therefore, capital D is also a variable. The area of a flow is also a variable in this case, and the diametrical parameters, it may be a breadth, it may be a diameter, it may be a width, it may be a height of a respective turbine, it should be taken as a variable in this case. Therefore, U proportional to capital D and N. That's why I have not considered capital D as a constant parameter in this case, because it is a geometrical parameter. Therefore, if you solve for this, D proportional to U by N proportional to, we know that U is proportional to root H, therefore root H by N, therefore capital D proportional to root H by N. Now in this case, we have a discharge Q is equal to area of the flow into the velocity of the flow. For a given turbo machines, I said that area of a flow is constant. Therefore, Q is equal to A proportional to V, pi d square by 4 into capital V, I can say. Now in this case, you just talk about, for a given turbo machine, area of a flow is constant, but while defining a specific speed which is geometrically similar, we are not supposed to consider the area of flow as a constant one. Therefore, Q proportional to D square into V. We have already defined what is the value of D, root H by N. Therefore, Q proportional to root H by N the whole square into root H. Therefore, Q proportional to H to the power of 3 by 2 by N square. So, in place of V, we can write root H, because the absolute velocity of the water is directly proportional to the square root of the head and the turbine. So, from the overall efficiency concept, we can write the power developed. It is the ratio of the power developed to the water power. So, we have a shaft power capital P divided by the water power rho g q into H divided by 1000 kilowatts. So, here I can say rho into G, it taken to be a constant one, and 1000 is also a constant one. Eta O, that is the overall efficiency, it's also a constant one. Therefore, from this expression I can write P is directly proportional to the product of Q and H. Therefore, which is proportional to, we have already defined the expression for Q. Yes or no? Therefore, take this into considerations, proportional to H to the power of 3 by 2 by N square into capital H, which is proportional to H to the power of 5 by 2 by N square. Therefore, P is equal to K into H to the power of 5 by 2 by N square. You call this equation as 1. Where K is the proportionality constant. You just remove the proportionality sign by introducing a proportionality constant. You just obtain the value of the proportionality constant by considering the specific conditions in a turbo machines. That is the important the thing which you need to do. Even in case of unit quantities also, the same thing we were doing. Yes or no? So therefore, we can, when we say this, when the head of the turbine is 1 meter and the power developed is 1 kilowatt, then the speed at which it is running is nothing but a specific speed. Yes or no? Therefore, geometrically or mathematically we can say that when H is equal to 1, P is equal to 1 kilowatts, capital N is equal to Ns, the specific speed of a turbine. If you substitute in the equation number 1, P is equal to 1 is equal to K into H is equal to 1, N is equal to Ns. Therefore, I can write K is equal to Ns square, or Ns square is equal to K. Just now I use the proportionality constant K and I defined the concept of proportionality using this. Therefore, the value of K is equal to Ns square in this case. So, I substitute the value of K into the equation number 1. Therefore, we will obtaining the equation for the specific speed. Specific speed Ns is equal to N into root P divided by H to the power of 5 by 4. This is the expression for the respective specific speed of a centrifugal pump. That is, Ns is equal to N into root P divided by H to the power of 5 by 4. So, now let us see what is the importance of the specific speed of a turbine. So when you see this the specific speed of a turbine, thus the specific speed of a turbine has been recommended to select a type of a turbine. For example, If I want for a particular conditions, I am a designer. I want to design a Pelton wheel with a single jet or Pelton wheel with a multi jet. These are all the type of the turbines, the Francis turbines and the Kaplan turbines. Okay, that means so depending upon the specific speed of a particular conditions, right? We need to recommend a particular type of a turbo machines. For example, if the range of specific speed required between 8.5 to 30. So we used to select a type of a turbine which is a Pelton wheel with a single jet. If it is 30 to 51, we used to recommend a turbine which is a Pelton wheel with a multi-jet. If the specific speed ranging from 51 to 225, the Francis turbine has been recommended. 225 to 860, Kaplan turbine has been recommended. Yes or no? That means, so depending upon the range of the speed, we are going to select a particular type of a turbo machines. Yes or no? So that's why when it talks about this specific speed of a turbine, specific speed is one of the important parameter which is used to select a particular type of a turbine for a specific conditions. Next I will talk about the specific speed of a centrifugal pump. So we have defined the specific speed of a turbine as specific speed is equal to n into root p divided by h to the power of 5 by 4. That is one of the important the standard equation for this particular centrifugal pump. Now let us see how we can define a centrifugal pump. So before defining a centrifugal pump, what is the objective of a pump? That is very important. So anyway, head is available. The main output of a pump is always the discharge. Whereas in case of a turbine, head is already available. The main objective of a pump is to develop a power. Therefore, head and the power are the two important parameters in case of a in case of a turbine. Whereas in case of a centrifugal pump, discharge is one parameter, head is one parameter. Take these two into consideration as specific parameters in defining the specific speed of a centrifugal pump. Therefore, the specific speed of a centrifugal pump can be defined as the speed of geometrically similar pump which could deliver 1 meter cube per second of discharge against the head of 1 meter. Technically, what does it mean? When the head on the turbo machine is 1 meter, or when the turbo machine is working against a head of 1 meter, under which it could deliver a discharge of 1 meter cube per second, the speed at which the centrifugal pump is running is called the specific speed of a centrifugal pump. As usual, when we go for defining the respective equation for a specific speed of a centrifugal pump, let us consider the tangential velocity. U is proportional to the absolute velocity of water. So we know this equation. U proportional to V, but V proportional to root H. Therefore, U is also proportional to V, proportional to root H. Tangential velocity of the runner, U is equal to pi dn by 60. As I said in the beginning, the geometrically similar concept means the diameter should not be taken into consideration, should not be considered as a constant one. Therefore, U proportional to capital D and N. Therefore, when you consider for the value of capital D, therefore D proportional to root H by N. This is one expression. As I said that we need to talk about the discharge. So we have a discharge Q is equal to area of the flow and the velocity of the flow. The product of area of the flow into velocity of the flow. Therefore, Q is equal to A into V. That is equal to pi into D into B into V. This is very important because pi dB is the area of the flow for a centrifugal pump. So where V is the breadth of the impeller. Therefore, for geometrically similar pump, I can say that the breadth, that means geometrically similar, the breadth or the width and the diameter, they should be taken as a common parameter for the centrifugal pumps. Therefore, I can write in place of B the value of capital D or the parameter D. Therefore, Q proportional to D square into V. Q proportional to, we have already taken the value of D, root H by N. So therefore substituted root H by N the whole square into V is equal to root H. You substitute that root H. Therefore Q proportional to H to the power of 3 by 2 by N square. You remove this proportionality sign by introducing a proportionality constant. Therefore Q is equal to K into H to the power of 3 by 2 by N square. When H is equal to 1, Q is equal to 1. You substitute, you call this equation as 1. So when H is equal to 1, Q is equal to 1 meter cube per second, the speed is specific speed. You substitute this value into this particular equation. So Q is equal to 1, 1 is equal to K into 1 by Ns square. Therefore K becomes Ns square. The value of the proportionality constant K equals Ns square. Therefore, if you substitute the value of the proportionality constant into the equation number 1 and rearranging the equation for a specific speed, we get specific speed n suffix s is equal to n into root q divided by h to the power of 3 by 4. This is very important. Okay. So when you are talking about this particular type of situations, right? So we have to see that how effectively we can define the specific speed of a centrifugal pump. Therefore, there are two options we have defined in this case. When a people wants to define the specific quantities with respect to a turbo machines, you cannot define a specific speed of a turbo machine in a common equation. No, it is not possible, because we must be very specific with respect to a turbo machine while defining the specific quantities. Because the specific quantity for a turbine is different, the specific quantity for a centrifugal pump is different. There is a specific speed. Because their basic objectives of the respective machines will be different. When we are defining a turbine, the power and the heads are the two important specific parameters should be taken into consideration. Whereas in case of a centrifugal pump, so there are two parameters. One is the manometric head, where head is nothing but the manometric head in case of a centrifugal pump, right? And that head should be taken into consideration. In addition to the head, so the second objective is to deliver a water or to discharge some quantity of water. Therefore, the discharge and the what you can say, the discharge and the head are the two important parameters that has to be considered while defining the specific speed of a centrifugal pump. So finally what we can say, the specific speed of a turbine is equal to ns is equal to n into root p divided by s to the power of 5 by 4, whereas the specific speed of the centrifugal pump ns is equal to n into root q divided by s to the power of 3 by 4. Keep this in mind. When a turbine is concerned, power is playing a major role. When a centrifugal pump is concerned, discharge is playing a major role. So taking this hint into considerations, we can definitely define without any confusion the specific speed of a centrifugal pump as well as the specific speed of a turbine. Now when we see the significance of specific speed, I said in the beginning of the concept itself, right? For selection of the turbine, it's very important. Specific speed plays an important role in selecting the type of the turbine. So what type of turbine we need to select for a particular condition depending upon this specific speed. So second issue is the specific speed is used to compare the merits of design between the two turbo machines. Say for example, we have already designed one concept. And we have another concept. There are two concepts which are available with us. I want to say which is the best design. That means merits of design I want to decide. Depending upon the merits of the design, right, I have to select a particular type of a turbo machines. Therefore, to compare the merits of design, we can use specific speed is one of the parameter. They are used for comparing the performance of turbo machines. There are two turbo machines are available. I want to say which is the best turbo machine, right? The parameter that we need to consider for this is the respective specific speed. Okay. Therefore, the performance of a turbo machines can be decided based on this particular specific speed. The performance of turbo machines can be predicted by knowing the specific speed of a turbine. That's also very important, a beautiful concept which we can expect from a specific speed, right? So if we know the specific speed of a turbine, right, easily I can predict what would be the performance of a respective turbo machines. Okay, they are used to define the availability of turbo machines for specific applications. Say for example, for one particular applications, if I want the specific speed of my design, so in between so and so, right? So what type of a turbo machines that we need to consider for that particular type of applications, right? So these are all some of the important issues which we have to consider for the selection of the respective type of a turbo machines. Okay, very important concepts. These are all the significance of a specific speed. Now, so in this session, dear friends, we discussed about a specific quantities related to a turbo machines. It may be a specific speed, it may be a specific speed of a centrifugal pump or a specific speed of a turbine. A specific speed of a turbine, n suffix s is equal to n into root p divided by h to the power of 5 by 4, whereas the specific speed of a centrifugal pump nsp is equal to h into n into root q divided by h to the power of 3 by 4, right? And the significance of this particular type of the specific quantities, right? So thank you my dear friends. So in the coming sessions I will be bringing you the more informations about the respective turbo machines. Thank you.